Okay, I hope to get through the last two properties of determinants. For A and B both square, the determinant of their product is the product of the determinants. The easy part of this, in a previous chapter, we said if, if either A or B is singular, meaning it doesn't have an inverse, then the product is also singular. And we already said that if a matrix is singular, its determinant is zero. So for singular matrices, this is obviously true. Either A or B is singular, that's zero, and so is this. You just get zero equals zero. Now, for when both A and B are not singular, then we use kind of a tricky approach here. We define this function, we'll just call it D of the matrix A. We'll define it this way. It's the determinant of the product divided by the determinant of B. Then we'll see if this little function satisfies the three primary properties of determinants. And if it does, then this little function is the determinant. Let's see if I go through this. So one of those with, if A is the identity matrix, then this little function D of A is just this, and it is one. That property is satisfied. If two rows are exchanged, then so are the same two rows of A, B. Two rows of A are exchanged, so are the same two rows of A, B. That was kind of a feature of matrix multiplication, leading to a sign change of the determinant of the product, and also to that function dA, so that property 2 is satisfied. Any linear combination of, say, row J of A leads to the same linear combination of row J of AB. Again, that's a feature of matrix multiplication. And since B is unchanged here in this function, property 3 also applies to that function. Anyway, that little function, this guy, satisfies all three properties, the defining properties of the determinant. So it is, in fact, the determinant of A. And you get this. What's the result of that? You had this, we already knew this, right? A inverse A is the identity. So the determinant is this product. And it's also the determinant of the identity, which is 1. So there you go. The determinant of an inverse is 1 divided by the determinant of the matrix. I'll get through this last of 10 properties, which is kind of important. The determinant of the transpose of a matrix is the same as the determinant of the matrix. It's a big deal because it means everything in properties 1 through 9 that we said hold for rows, they now hold for columns. The easy case is if A is singular, then so is A transpose, and just get 0 equals 0, that property satisfied. If A is not singular, then you can do row operations without row swaps anyway. It says you can break up your matrix, original matrix A, into a lower triangular matrix and an upper triangular matrix with all the non-zero entries on the main diagonal. Well, U has all the non-zero entries on the main diagonal. Let's see, L is lower diagonal and all the diagonals equal 1. Then we'll look at properties 9 and 7. Let's see. So A can be broken up into this LU. And by the previous property, that's the product of these two determinants. But L is triangular with all 1s on the diagonals. So its determinant is 1. leaves us with this. A transpose will be if, the product rule for transposing. By the previous property, it can be broken up like this. And again, this guy, even when you transpose it, just flipping it around a main diagonal, it's still triangular. So that determinant is 1. With this, but it is triangular. So the determinant of that is just equals 2. And up here we said that equals A. Anyway, that's the proof of that if you don't do row swaps. If you do row swaps, it's kind of more complicated, but you end up with the same result, and I'm just going to skip that. We'll summarize them all in another video.